Hi, in this video I will be talking about complex numbers, and I just want to give a warning that some of the material in these notes might not be things that I actually cover in class each year. So if you missed class and you're watching the video, just compare this to what homework has been assigned and you might notice that some of these topics aren't coming up. But in the video I'm being a little more complete because from year to year I might cover different things. So just to set this up, there are cases, for example, maybe we're completing the square and imagine that we're at this stage and we have this equation. So we want to take a square root of each side. But we realize that square root of negative 25 isn't something that we can actually do. So we kind of hit a wall, and typically we would just say, oh, there's no solution. Right? I tried to do this and there's no solution. Sometimes we might say there's no real solution. Right? And that's true. There's no real number that makes this work. But still, if we extend our notion of what is possible with numbers, we can make a little bit of sense of this. And this might feel a little bit silly. It certainly feels abstract, but there are genuine uses for it that I will hint at towards the end of this section. So the idea is we're going to talk about a new class of numbers called complex numbers. Even the name here suggests there's something rather complicated and exotic about them. And they're based upon a number whose square is negative 1. So that's our jumping off point. We want to somehow think about taking square roots of negative numbers. If we imagine I want to take the square root of negative 1, right, that's essentially asking what is the number where when we square it we get negative 1. And no actual number has that property. No matter what you try, you'll never get a real number where you square it and you get negative 1. So what has been done here is mathematicians have actually decided, well, let's cheat a little bit. If there's no actual number that has this property, let's make one up. And since it's not actually a real number, we'll call it an imaginary number, right? We're just going to imagine that somehow theoretically there's this weird imaginary kind of number that makes this correct. That if I square that number, I get negative 1. It's definitely not a normal number, so we can't actually write it with digits. So by definition, we simply call it lowercase I. And by definition, we say it is a number where if you square it, you get negative 1. It's not an actual number you would see on the number line. It's something we have to imagine. It's an imaginary number. But once we're open to the idea that there are imaginary numbers, we can start evaluating other kinds of expressions. So for example, the square root of negative 9, using our normal rules, we could say is the square root of 9 times the square root of negative 1. So that's 3 times, well, square root of negative 1 now has a name. We're calling it I. So the square root of negative 1 is I. The square root of negative 9 is 3I. It's like, oh, take the square root of 9, but create the imaginary version. Similarly here, this would be 5i. Square root of 25 we know. Square root of negative 25 is an imaginary version of the same number. Square root of 100 is 10. Square root of negative 100 is 10 times I, because it's the square root of 100 times this imaginary thing, which is the square root of negative 1. And a complex number is a number of the form a plus bi, where a and b are real numbers. The idea is it's what happens if we start combining regular real numbers with imaginary stuff. Okay, and sometimes we say pure imaginary number. A way of visualizing complex numbers is on what's called the complex number plane. And what we would do is we would say if I have the complex number a plus bi, I would plot it as though it were a comma b. So just as a quick example here, we would say, for example, the point 3 comma I, 3 plus I is like that. Because 3 plus I basically is 1, 2, 3 units in the real direction and 1 unit in the imaginary direction. 1 minus 2i would be like this. We go 1 in the real direction and minus 2 in the imaginary direction. So there's no number line for complex numbers, but there's a number plane. And a bit of vocabulary that sometimes comes up when people get into these is the absolute value or modulus of a complex number. Basically represents how far is that complex number from 0. Right here would be 0, which is 0 plus 0i if we want to be really fancy. And so one way of thinking about how big a complex number is how far apart is it from 0 in the complex plane. We mark it with vertical bars, just like we would do for the absolute value. And the formula is it's the square root of a squared plus b squared. And let's just notice a and b are the real parts. So don't square b times I, don't create any negatives, just a and b, the actual real numbers you see. Okay, so pause, or actually I'm going to do this one, right? So how could we plot 3 minus 4i? So we would imagine going 1, 2, 3 units in the horizontal real direction and 1, 2, 3, 4 units in the imaginary vertical direction. And it would be this point here. Right? It's basically like plotting 3 comma negative 4. And its absolute value is simply this distance. Really all we're doing here is Pythagorean theorem. We went over 3, we went down 4 imaginary units, but still it's a distance of 4. And if we're trying to find this modulus here, we're just saying 3 squared plus 4 squared equals m squared. So m is the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. So try that with these last two. Plot where would this be on the complex plane, and then how far apart is it from 0? That is what we would call the absolute value or modulus of that complex number. All right, I hope you've tried that. 3i we can think of as 0 plus 3i. We're just going above our center point. So this is where z2 is. And hopefully you see without even a formula, well, that's 3 units away from 0. For this one, we would go 8 units backwards in the real direction and 6 units up in the imaginary direction. It would be here. To compute this distance, it would be the square root of negative 8 squared plus 6 squared. Not 6i squared, just 6 squared. That's the square root of 64 plus 36. Square root of 100 is 10. Right? That's 10 units away from the origin. Now, something we really want to focus on is that complex numbers are numbers. And like with numbers, we can do arithmetic. If I have 2 numbers, I can add them together. If I have 2 numbers, I can subtract them, I can divide them, I can multiply them. Same with complex numbers. When I have complex numbers, I should be able to do these numbery things to it. So if we're just adding or subtracting, it's like an algebra problem. If you can algebraically do something like 3 plus x minus 5 minus 2x, understanding that the numbers are like terms and the x things are like terms, then adding or subtracting complex numbers is exactly the same idea. So for this example here, first thing I would distribute that negative. So I would have minus 5 and minus 3i. Then I would just group like terms. 4 and negative 5 are both real numbers. I can combine them and I get negative 1. Negative 1 and negative 3i are both imaginary. I can combine those and I get negative 4i. You don't even have to worry about what I means, just combine them. So take a moment and try these two examples below. For this one, again, we would distribute that negative, and when we combine like terms, the real part would be 4, and the imaginary part would be 6i. Here we don't need to distribute anything, just the real part would be from 2 plus negative 1, which is 1. The imaginary part, we have 3i here and 9i here. That makes 4, 12i. Just like algebra. Whatever I is, just treat it algebraically. Now, if we multiply two complex numbers, we again just treat it like it's algebra, except if I squared emerges, we'll remember that I squared is equal to negative 1, and that will let us simplify, because we want to give answers that have this form. We don't want an I squared in there. We want to do better. So let's look at this example. If I just did this as a foiling problem, first would be 3 times 4, which is 12. Outers would be 3 times 3i, which is 9i. Inners would be negative I times 4, which is negative 4i. And lasts would be negative I times 3i, which would be negative 3i squared. But this is where we would say, oh, I squared is the number negative 1. So I really have minus 3 times negative 1. And minus 3 times negative 1 is 3. So now I'll group my like terms. My real numbers are 12 and 3, which make 15. My imaginary ones are 9i minus 4i, which is 5i. So it's basically algebra, but when you see an I squared, remember that that's equal to negative 1. So try these two. All right, I hope you've done that. Hit pause if you need more time. Here, when I FOIL, I get 2 plus I plus 8i plus 4i squared. I'll just combine those imaginary things in the middle. 4i squared is really negative 4 because I squared is negative 1. So if I combine my real numbers, I'll have negative 2 plus 9i. Here, I can just distribute. I would have 8i minus 2i squared. I squared is actually negative 1. So I have negative 2 times negative 1, that's 2. And usually we write the real number before the imaginary one. Now, division is a little more complicated, so there's something we need to talk about. By definition, complex conjugates, oops, I don't know what happened there. Complex conjugates are a pair of complex numbers where one of them is a plus bi and the other is a minus bi. So they're almost the same. They have the same real part, but they have opposite imaginary parts. So this would be an example, 3 minus 2i and 3 plus 2i. The 3 is exactly the same. The real part is exactly the same. But the imaginary parts has one positive and one negative. Now, pick your own example, it doesn't have to be this one, and multiply them together. Hit pause and actually do that. So I'll do an example. I will do the example 4 plus 5i times 4 minus 5i. If I FOIL, I get 16 minus 20i plus 20i minus 25i squared. Negative 20i plus 20i, that just cancels. Oops. And then remembering that I squared is negative 1, what I have here is plus 25, and my whole answer is 41. So I took these two complex numbers and multiplied them together, and I got what looks like an ordinary, typical real number. And that's worth remembering. That will always happen if you do it correctly. If we multiply together a pair of complex conjugates, we will get a real number. All the i's will go away. So if we remember this, this is a tool for doing division. So let me show you an example, and then I'll point out how we followed these steps. Suppose I wanted to do this division. I'm taking the complex number 2 minus I, and I'm attempting to divide it by the other complex number 4 plus 3i. We want to simplify this. What number is this? This doesn't look like a complex number. It seems too complicated. We can make it less complicated. So the trick is to remember this fact we just learned about complex conjugates. In the denominator, I will think about that complex number and I will multiply by its complex conjugate. And I will do the same thing in the numerator. So I will FOIL out the top. When I FOIL out the top, I get 8 minus 6i minus 4i plus 3i squared. When I FOIL out the bottom, I get 16 minus 12i plus 12i minus 9i squared. So now let's simplify. Here I would have 8 minus 10i, and 3i squared is actually negative 3. Here, as planned, if I did this correctly, the imaginary things just cancel. This is 16. This is actually positive 9 because I squared is negative 1. So let's keep going. In the numerator, I have 5 minus 10i. In the denominator, I have 25. And now let's just break this up. This is really 5 over 25 minus 10 over 25i. So in our simplest form, there are fractions involved, which is not a shock given that we did division. But we're able to express this in what we're used to for a complex number. We just see this real number, and then we're adding or subtracting this imaginary part. We took something that was more complicated. It had i's in the numerator and the denominator, but we were able to get it in terms of here's the real thing, here's the imaginary thing, and we're just adding or subtracting. So what did I do here? First is that I wrote the division in fraction form. And the focus is on the denominator. I looked at this denominator, 4 plus 3i, and I asked, what is its complex conjugate? Then I multiplied top and bottom by that conjugate. Make sure you do both. Right? FOIL out top and bottom. You can FOIL out the bottom, but there is this shortcut here. You might notice that what I ultimately got in the bottom was 16 plus 9. The 16 came from the 4s, the plus 9 came from the 3s. If you do that, you'll then have just one single number in your denominator, so you can break up the expression and write it as two different fractions. So try this example. Hit pause and give it a shot. Okay, so we focus on the denominator, whose complex conjugate would be 2 plus I. So we'll multiply top and bottom by 2 plus I. I like to add in those parentheses so that it looks like foiling. So in the numerator, when I FOIL, I will have 6 plus 3i plus 4i plus 2i squared. In the denominator, if I remember that shortcut, it's basically just 4 plus 1. What do I get from squaring 2? What do I get from squaring 1? Because I basically have 1i and negative 1i. So what do we have? This thing here is just the number negative 2. So if I simplify the numerator, 6 minus 2 gives me 4 for the real part. 3i plus 4i gives me 7i for the real part. And I have the number 5 in the bottom. So now let's just break this up. This is 4/5 plus 7/5 I. Yes, it has fractions. We did do division. But we've written it as a real number plus an imaginary number with no additional complexity. Now, why do we care? As hard as this is to believe, legitimate math can be done here. So I'm not going to go into the details, but if you get to calculus and you start learning advanced differential equations, this is one case where this happens. There are other places where you have a real problem, right? An actual word problem where everything makes sense in the real world. And then you apply known methods. You say like, oh, I've seen problems like this before. I know what I'm supposed to do. Then it seems like imaginary numbers emerge. You're doing your normal things and you need to take a square root of a negative and it feels like now your problem is meaningless. But then you just keep going. And in many cases, you keep following the steps and all of the I imaginary stuff cancels. And you get a real, meaningful solution. So you kind of have to wade through the land of complex numbers in order to follow all your steps. But then you notice all that imaginary stuff kind of goes away by the end. I can't give you more detail. But later on in your mathematical career, you might notice complex numbers coming up in a way that actually feels helpful. What I will also tell you is it allows us to solve difficult quadratic equations in a way that's a little deeper than just throwing up our hands and saying there's no solution. So suppose that I asked you to solve, not solution, solve, say the equation x squared minus 6x plus 10 equals 0. And then suppose that I add an additional instruction to simplify any complex solutions. Let's try completing the square. I'll move the 10 to the other side. By completing the square, I'll add a 9 here, so I'll add a 9 here. So this is the x minus 3 quantity squared. This is negative 1. So we would say x minus 3 is plus or minus square root of negative 1. But now, when we get to a step in a problem, you'll see this in quadratic formula quite often. If you get to a step in a problem where you're taking the square root of negative 1, you can now make sense of that. We can say, all right, well, I have a name for that. I'll just call this I. And technically, there's a positive version of I and also a negative version of I. So maybe x minus 3 is I. Maybe x minus 3 is negative I. So maybe x is 3 plus I. Maybe x is 3 minus I. So these are the complex solutions. There is no real number that makes this original equation true, but there are complex numbers that make it true. And I could actually demonstrate that. So just as a demonstration, suppose x is 3 plus I. X squared would be 3 plus I times 3 plus I. If I FOIL that out, I'm doing this rather quickly. You wouldn't need to do this, but I want to convince you that it's true. This part here is positive 1. So x squared is the complex number 10 plus 6i. Minus 6x would be negative 6 times 3 plus I. which is negative 18 minus 6i. Give me a second. Oh, sorry. I see what I did. So this should be just plus I squared here. And then that's an 8. I knew something was a little fishy. So now what we'll notice is x squared minus 6x plus 10. Well, we just saw that for this value of x squared is 8 plus 6i. Negative 6x is negative 18 minus 6i plus 10. If we group our like terms, well, our real numbers are 8 minus 18 and 10, that's 0. Our imaginary stuff is 6i minus 6i, so that's basically no imaginary things, and we really do get 0. If x is this number, if x is this non-real number, this complex number, it really is true that this is a number that makes the equation x squared minus 6x plus 10 equals 0 true. All right, that is it for this video.